stored charge. We call this as capacitance. Now, whatever device which stores this, we call that device as a capacitor. Now, two quantities of which we have already learned of, right? One we have learned about charge, electric charge, right? And one we have learned about potential. Both the quantities we are aware of. So when we take the ratio of charge and potential, the quantity that we get is known as capacitance. So you can define capacitance as the ability to store charges or electric potential energy, but you can also define it as the ratio of the charge and potential. So according to it, one capacitance, right, values, one will be equal to 1 coulomb of charge divided by 1 voltage, because capacitance is what? This is the ratio of charge and voltage, right? So this is it. So yes, 1 coulomb by 1 voltage, we have a specific unit for it, which we called farad. So 3 farad, 5 microfarad, 3 nanofarad, like all this, we write the SI unit of it. This is a slide important to you, capacitance of conducting sphere. So in this, what will happen? You do not have to go through the procedure. Now you just have to remember the final formula, 4 pi epsilon naught r. 4 pi epsilon naught r, this is valid for any sphere. If you have a conducting sphere, you will directly use C is equal to 4 pi epsilon naught r. If some modification is there in this question, it will let you change the potential. So whatever is the new potential that is generated, accordingly you put it in this. As in, for example, right now you have a conducting sphere, and you know for a conducting sphere, the potential is kq by r, right? You know it, that is kq by r. So if this is kq by r, suppose, let's say we have a sphere whose value, whose potential's value you already know, right? Or whose formula you know. So what will you do? You'll put it in the derivation part here. So as such, you do not have the derivation part involved, this kq by r, like this, right? So instead of kq by r, whatever is the potential for it, whatever is the potential of it, that you can put it in that manner. And so you will have the conclusion, but we only have it for conducting sphere, and usually this is only asked. So C is equal to 4 pi epsilon naught r. This you have to remember. Put in the proper radius of r. If Earth is asked, if Earth is acting as a conducting sphere, then do not waste your time in the calculations. Directly remember the value 711 microfarad, right? This value 711 microfarad, do remember this value as it is, because you will substitute all the same things only, unless and until it is specified or a modification has been made in the question. Use put in the value of capacitance if Earth is acting as it. If this can be difficult when it can relate this to your gravitation. It will give you such modifications where the radii of Earth is changing. So using your gravitational concepts, or whichever concepts of gravitation you are aware of, use those to get the new radii, and then put the new radius into the formula and see whatever value you're getting. Unless and until specified, you're going to directly put 711 microfarad. Fine. So whenever you have a question related to Earth's radius is asked, and certain slight modifications are given, do relate it with your gravitation. Check whether the radius is the appropriate radius or not. Then we have capacitor. As I was telling you, capacitor, this is a device that is used to store charge. So how is capacitor created? Just take two, so you just have to take two conductors, fine? Two conductors are sufficient. Charge one as positive, other as negative. So opposite charges are constructed. There should be a dielectric medium between them. What is a dielectric medium? Insulating medium. It won't allow the charges to pass through it. Fine, that is a dielectric medium. So two conductors, they have opposite charges with dielectric medium within them. So this device that is created, this is known as capacitor. Fine. Depending upon the shape of the conductors which you have taken, have you taken cylindrical cylinders, have you taken direct plates, or you have taken spheres and then have charge, that will define your type of capacitors. All right. So you have all the types of capacitors important for JEE exam. cylindrical as well, spherical as well, parallel plate capacitor. Parallel plate capacitors are very basic that you have to understand, and you have to learn all the formulas and all the cases of it. Spherical capacitor can also be asked, and cylindrical capacitor is also asked in your entrance. That was not important from your board exams perspective. Only parallel plates were asked, but now in JEE, cylindrical capacitor, single formula is there that can be used. All right. Then you have principles of capacitor. This simply says that wherever you decrease the potential, somehow capacitance will increase. And how can you decrease the potential? By earthing it, bringing uncharged earthed conductor near it. Fine, this is not so very important. Here, yes, parallel plate capacitors, all the formulas. Class, this derivation, this was there in your board exams, right? Now see, this derivation part is not in, derivations are not asked, right? You do just have to remember the final formula. But the steps in each of these you have to remember. Because the questions can be modified, sigma can be variable, plate number of plates can vary. So what you will do? In the steps, wherever you are placing every physical quantity, there you will make the modifications and see whatever final answer you're getting. So derivations, steps of these parallel plates you have to remember. I'll also show you a question, one same question, similar question appeared also. So we'll discuss that. So what all steps? Some basic steps that you have to remember, and that will define your final answer. First, the electric field. Electric field we have studied also. Electric field you have to remember. Calculate all the electric field that is appearing. For plate 1, for plate 2, whatever plates are given, just calculate the electric field. See finally what all electric field you are getting in the conclusion. You will be getting sigma because parallel plates, we know using Gauss law that sigma by 2 epsilon naught will be involved. So instead of sigma, write what is sigma? Surface charge density is what? This is charge per unit area. That is charge divided by the area. So Q divided by A, that will be sigma. Fine, Q divided by A is sigma. So now you have to put in the value, right, of sigma. So in this way, this becomes your first step. Then you know one relation, E is equal to V divided by D. Right, E is equal to minus dV by di. I have told you that this is directly also asked, has theoretical importance as well as it has numerical importance. So same way, V is equal to ED you can write. Now, value of electric field you have already calculated, just multiplied by the separation between the plates, whatever is the separation given. So now modifications can be in these steps only, like distances half, right, or distances tripled, or any such value is given. So like this, you can just whatever is your electric field you are getting it, multiply it by D. Fine. Then you have capacitance. Now, potential you have calculated. You have the whole potential with you, electric field into D, separation. Now, simply write the ratio of the charge with the potential what you have obtained. Whatever is the potential you have obtained just now, divided by. Fine, charge by potential, you get the capacitance. So these are the basic steps for the derivations. But for your numerical also, whichever numerical you'll get, in whichever step the modification in the question is given, use it, write it. Then you will get your final answer. Even if the values are asked, you put in the values in that manner. All right, so this was, so yes, formula also you have to remember. Formula wise, I'll tell you at the end. Same way. Yes, this part. See, if two parallel plates are there, two parallel plates, they are kept. So, and they're completely filled with air. No other medium you have kept, oil or water, nothing is there. They are just completely filled with air. So, value of capacitance will be epsilon naught A by D. Fine. If it is filled with dielectric medium, whatever is the value of dielectric constant, you will multiply it with it. Whatever is the value of the dielectric constant, simply multiply it. All right. So K times it will become whatever is your original value. Let's say C naught is the original value. So you will multiply it with K. So KC naught it will become. So your capacitance will anyhow increase by K times. All right. Now, if a dielectric slab is not completely filling it, it is partially filling it. filling it. It means some spaces are left above and below the dielectric slab. So in that case, if let's say the thickness of the dielectric slab is some T, what will be the formula for it? Epsilon naught A D minus T plus T by K, right? If this is asked, this will be a little general. Modifications are usually not given from this part, partially filled. But from your normal epsilon naught A by D, the questions can be modified. They can be tricked. Then you have C is equal to epsilon naught divided by D minus T. That is, if whatever was the thin strip which we were filling with dielectric, instead of it, if we replace it with a conductor. So partially filled conductor will be epsilon naught A by divided by D minus T, where T is again the thickness of the conductor. Right? So T can be the thickness of dielectric slab, conductor, whatever is given. Accordingly, you have these formulas. These formulas you have to remember because these are the basics of it. Then direct energies formula, remember it. These will be related, these can be related to your potential energy, kinetic energy. Remember all the three formulas. Remember one of it, substitute it. Half CV square, if you know, you can put C as Q by V, you can get half QV. You can then again replace it, you can get half Q square by C. So all the three formulas of energy you should remember: half CV square, half QV, half Q square by C. But at least you should remember the most important out of all these also is CV square divided by 2, half CV square. That is very important, half CV square. But just remember one, then you can substitute. So yes, spherical capacitors, right? So spherical capacitor, this is the formula for spherical capacitor. So in spherical capacitor also, just remember the formula: 4 pi epsilon naught R1 R2 divided by R2 minus R1. That's it. This is the simple basic formula. 4 pi epsilon naught R1 R2 divided by R2 minus R1. All right. Derivation you don't need to do. If radii are equal, then you can put R1 as equal to R2 and see whatever answer you're getting in. Directly it is R2 minus R1. Fine. So if it is not concentric, this is actually mainly, this is used for concentric only. Yes, class, this question, that is calculate force between the plates of capacitor. You learn the formula that is given, or the final formula that is given at the end, this final formula, which is this is a question form that comes in your board exams. But F is equal to minus Q square divided by 2A epsilon naught. Just remember this as it is if force is asked, because otherwise you will have to use it. And yes, class, how the questions can be built up from this topic is that forces formulas will be different. QE is also there, right? One is your gravitational force, also mg. So many values of forces you have, right? So those values of forces will be there, and then you will be equating all the values with this if some variable is unknown. So just check in your isolated system if net force is cancelling each other, both the forces will be equal. Whatever force you have calculated from other topic, from other formula, equate it with the electrical one. All right, that is about force. And then you have to remember about electrical energy density. See, regarding energy density, just remember this fact: for energy densities, wherever the term density is written, usually we write the term density when we are dividing something by volume, when something is per unit volume. So for energy density, we'll write energy per unit volume. Now energy's formula, we have already seen the three formulas of energy. So energy's formula, if you already are aware of energy's formula, then do one thing. Whatever formula you have, you can use it. But see, class, it's better for energy density also if you remember the final formula. The final formula is also sufficient, because this doesn't get modified much. You mainly have this half, use this half E square epsilon naught. Yes, comparison can be made between the magnetic energy and electrical energy. There you will have magnetic field. Instead of permittivity, you will be having permeability. So that is different. So half E square by into epsilon naught. Sharing of capacitors is very important. This is a very important topic when you are revising capacitors after parallel plate and all those basic formulas. Do have a look at sharing of capacitors. Questions have been coming from this topic. There are a lot of chances that questions will come from this, especially common potential questions type. We'll see questions also. Common potential questions are also included. So common potential is what? Two capacitors were there. They are now connected. One single potential will be generated. If they are connected in parallel, one single potential will be generated. That is the common potential. So here also, this formula is enough. C1 V1 plus C2 V2 by C1 plus C2. But I'll suggest you, instead of remembering this formula, no, common potentials formula, it's better if you remember by charge before sharing is equal to charge after sharing. That's enough. Charge before sharing is equal to charge after sharing. Whatever you are getting the charge before the capacitors are connected, add it, keep it aside, check what is your final answer when the capacitors are connected, and then you can equate both of these to form the common potential. All right, so that is how you can calculate it. And it's better if you calculate it in this way, because the charges, they are related to your circuits can be then changed and modified, right? So for that you have common potential. And yes, loss of energies formula, directly remember this formula. Remembering of this formula is enough. There are no such steps where you can there is a need of derivation. So directly C1 C2 into V1 minus V2 whole square divided by 2 C1 plus C2. This is the energy that you will get. Fine. This is simply this formula. Remember it. If this directly comes, this formula, loss of energy, then the values will be tricky. It will be the values will not be so easy to calculate. It will just be the values will be a little more in decimal form, so that calculations will become lengthier. Otherwise, common potential is more important than loss of energy. Sharing of capacitance. Fine. So this is about simple capacitance when single plates are there, when single capacitors are there. If we connect them, so combination of series and combination of parallel you get, but capacitors can isolated or can also be asked to you in isolated manner. But capacitor along with inductor, along with a resistor, there are a lot of chances that capacitors concept will be used in electromagnetic induction. Fine. So in EMI, you have the circuits. In AC also, especially AC, you have all the circuits, right? LCR and all. So capacitors will be, this whole concept of capacitors, if not asked individually, they'll be asked in the form of questions. Fine. So this you already know, series formula, parallel formula. For series, you reciprocally added 1 by C1 plus 1 by C2 till up till 1 by C equivalent. And for parallel, you directly added C1 plus C2 plus C3, like this, keep on adding it. Fine. So that's all about the theory part. What you should remember. Some numericals, let us practice what all numericals we can do and what have recently come. We'll try to cover the recent one, because the earlier questions that have come a long time back, they are just directly based on parallel plates capacitors formula, and they are based upon the direct circuits where they are in series or parallel or one is missing. Let's see whichever questions are there. First question I'm writing. So again, write it along with me. Try it yourself. Whichever option is according to you correct, write it. Let me know in the chat box. Whoever gets the answer, please let me know in the chat box whatever is your answer. See, class, this is a very similar question to what I was telling about the derivation part for parallel plates, right? So it says that if QF is the free charge on the capacitors, right? And QB is the bound charge on the dielectric slab. K is the constant that is placed between the capacitors. And what is the value of bound charge? Q not me, QB. QB can be expressed as. So values of QB. So look, you will directly use the formula. What will be net electric field? If you have, let's say, suppose if you have two parallel plates. So one will be positively charged. This will be negative charge. So there will be a net electric field as well. Fine. So electric field, you'll put it. What will be the electric field? See, electric field's value, this you know already. This is sigma by epsilon naught. So net electric field is actually equal to E naught with air minus EK with the dielectric constant. So E naught will be sigma by epsilon naught. This is actually of the bounded one, right? Equal to sigma free. Why I'm writing sigma? Because QB, QF, I can equate it with sigma divided by epsilon naught minus sigma F divided by K times epsilon naught, right? So epsilon naught will get cancelled, but before we cancel it, sigma is equal to charge divided by area. Now, area for B and F, we don't have to write, bound and free. Area is one single that we have to write, right? So this will be what? Sigma will be bounded charge by area epsilon naught equal to free charge by area epsilon naught minus free charge by K epsilon naught into area. So similarly, what will you get? Area epsilon naught, this will get cancelled. QB will be equal to QF 1 minus 1 by K. That's it. So which option was this? B, I think. B option. So B option is the correct option. Note it down, then I'll share some more questions.
Ma'am, why do we say that E net is due to the bounded charge?
The E net is due to the bounded charge because this says that question is saying what? QF is the free charge on the capacitor plates and QB is the bound charge on the dielectric slab of electric constant that is placed between the capacitor plates, right? So if I tell you where is the net electric field line, E naught, if I say this is sigma F, that is whatever is the free charge divided by epsilon naught. When I talk about K, dielectric constant, that will be sigma by K epsilon naught. So here what is happening inside within this, you are having EK, that is electric field, having the value K times, right, with a dielectric slab. So net electric field is what? Net electric field is because of all the free charges. That is ultimately giving you the bound charge on the electric slab because electric slab is kept within. So all electric field due to all the free charges will be the net electric field. That is with the free space minus without the dielectric, whatever is left. The space within the plates with the slab. So that becomes your net. So that's why instead of writing this separately, we will write this net electric field. This is actually, the question is also giving you a hint when it says no free charge and bound charge. Free charges, these are residing on the capacitor plates. When their difference is taken along with the dielectric one, slab one, that is your net electric field which you are getting in. That is making your whole charge bounded onto the dielectric slab between the capacitor plates. Fine. So that's why bound charge, always write it as the net electric field. Because in this question, this is not generalized. Don't make this statement generalized that we always write this specifically in this question, because no other value and no other data is given. So we know that this is the simple case. Here E net is there. Here also you will be having K. That's it. Here you will be having K. EK will be existing between this. So E naught is electric field without it. EK is electric field with. So that will be the resultant. Fine.
Yes, ma'am.
Yes, Marita, right answer. Correct option. See, total charge on both capacitors will be what? If I ask you about the total charge, Q1 plus Q2 you will do. But we do not have charge specifically. So Q is equal to CV is the formula. Use it. C1V plus C2V. I have told you, initial charges is equal to final charges. If you use that, that is much better. So C1V plus C2V. What is your C1? 2CV plus CV. So that becomes 3CV. Yes, Adriel. Correct answer. This is 3CV. So when dielectric material is filled within the capacitor of capacitance, after removing the battery, charge remains same, but capacitance becomes K times. Right answer, Priya. So what will be the common potential? Charge divided by K times C plus the 2C which you have. And what is K times C? That is 3CV divided by KC plus 2C. So CC will get cancelled. So we only have 3V by K plus 2. So yes, correct option is C. There's also like Marita, she has given me the value of x written. So write whatever numbers you're getting it. Krishna, check your calculations once again. Marita, now the second one which you have given, that is accurate. At here you can round it off. Instead of writing no 0.9 at the end, you can just round it off the number because the single digit x is exact value, that is right. And yes, Marita, the second one which you have sent, that is the exact answer. Plus, this is a direct formula based question. Those who are not able to do, see directly formula you will use. Apply the formula for this. Capacitance will be space is filled up to thickness, means some space is left. Total separation was 10. This is only covering 5, means 50% of space is still left. So you will use the formula epsilon naught A divided by D minus T plus T by K. That's it. Area, you know that is 100. D is 10. Thickness is 5. K is 10. So if you put in the values, 100 into 8.85 into 10 to the power minus 12, 10 minus 5 plus 5 by 10. So this is equal to 161 into 10 to the power minus 12 farad. That is 161 picofarad. So till now only Krishna's answer is correct. Yes, Priya and Krishna are correct. See, class. Here you just have to go by the parallelogram law or vector form. See, this will be the pendulum, right? This will be the pendulum. Why will this be the pendulum? Because see, net pendulum is oscillating between the capacitor's plate, right? So at one end, if this is coming, so see, this is QE getting attracted because of it. Downwards, this is mg, right? This is mg. And here you will get down their resultant acceleration, no, right? Their net acceleration will be here somewhere. So see, what is the net acceleration? If you look here, the net acceleration, this will be a1 square plus a2 square under root using your parallelogram law. So that becomes g square plus QE by m whole square. How QE by m? F is QE, acceleration is F by m. So this is QE by m. Now you know time period's formula. This is acceleration. So time period is 2 pi under root L by G, we write, but here we'll use the net acceleration. So your answer will become 2 pi under root L by G square plus QE by M whole square. So A option. All those who have given A option, their answer is correct. Others noted down. T class, it says that voltage rating of parallel plate capacitor is 500 volt. Then it says that, yes, Marita, right answer. Then it says that its dielectric can withstand a maximum electric field of 10 to the power 6 volt per meter. Plate area is given 10 to the power minus 4 and dielectric constant if the capacitance is 15 picofarad. So capacitance's formula is K epsilon naught A by D. From here, you already have the value of electric field as V by D. So D will be equal to V by E. D's value is V by E. So value of K will become what? K will be CD. So that will become CV divided by epsilon naught A and that electric field which is left. So because D, instead of D, we have substituted V by E. CD epsilon naught by A. So CV by E epsilon naught by A. Now all the terms you should know what are the values of all these terms. Capacitance is 15 into 10 to the power minus 12. Voltage is 500 divided by epsilon naught. Area 10 to the power minus 4 you have. Right? And this is 10 to the power 6 is electric field. So this value will be around 8.5. That is the B option. If two capacitors are there, this is one capacitor C1, 120 voltage. No, Krishna, check again. And this is another capacitor with 200 voltage. See, for potential to be made zero after connection, charges have to be equal of both are equal. So what is charge 1? Charge 1 is 120 C1 and charge 2 is 200 C2. So 3 C1 is equal to 5 C2. Option A or B? B. B option is right. Note it down. All those who will write it, text me done in the chat column.
Ma'am, can't we use the common potential formula?
Common potential, if you use, then you don't have the value of common potential. So how will you get the value?
And 0 is common, right?
Yes, for the final potential, if you equate it. So by that also you should get the same potential, because potential on each, it is written in the question. What was written in the question? Potential on each made. So two capacitors, they are charged to 120 respectively. It is found that by connecting them together, potential on each one can be made zero. Yes, that will be the common potential. So by using that, you're getting a different answer.
Yes, ma'am.
What is the answer that you're getting?
C.
5C1 plus 5C2. C for common potential if you're using it. So C1 V1 plus C2 V2 divided by C1 plus C2. This C1 plus C2, this will also become 0, right? Because this is common potential is 0. So C1 into V1. So that is 120 C1. How are you getting this? This is not getting reduced, no? This.
Ma'am, we can bring it to the other side. Then we can cancel the common.
Then also it will not get reduced. See the calculation? It won't get reduced. Problem is that 120 C1 plus 200 C2 is 0. Right? Then you will have one term as negative of the other. Then also you'll get the same thing. See, if you take the magnitude, if you bring that on the other side, this only you'll get at the end.
Ma'am, but it would be negative, right?
It would be negative. Then it would be negative. But here, since only magnitudes are given, so you'll get the same formula from that term. Because here we do not have any considerations about signs. Minus, plus, nothing is given. Because we do not know the capacitance's value. If capacitances are put, then whatever will neutralize it. Because right now we are just having the charge. So that would be, if it is negative, one would be, it means that one of the charges are negative. Right? It means that one is negative. If one is, this basically means when they are connected, this is plus minus and this is minus plus. If by using common potential, one is coming negative, no, on the other side, this means this is plus minus and this is connected in this